All right, in this class, we're going to begin our study of convergence tests. These are theorems that will help us decide whether or not an infinite series converges. Does the infinite list of numbers added together equal a finite number, or does it equal infinity or negative infinity? The very first page of your packet has a list of all the convergence tests that you're going to be learning. So today we're going to talk about the integral test and actually we're going to talk about the P-series test, the nth term for divergence, and the integral test. We did geometric series last class. So we're going to get about halfway through this table today. Okay, so recall that a series converges if the sum of all the terms is finite. So I'm going to look at this series. It's an infinite number of terms. I'm summing an infinite number of terms. And I want to decide, could this possibly be finite? Is it finite or is it infinite? So we're just going to write out the first several terms. So it starts with n equals 1. So I'm going to plug a 1 in. And you get 2 minus 3 times 1 squared. So the numerator is -1. And the denominator, you plug in a 1 and you get 5 plus 9, which is 14. -1/14 is the first term. The second term, you plug in n equals 2. So you start with a 1 and then a 2. So when you plug a 2 in for the n's, you get -10 over 29. And then you plug in n equals 3 and you get -25 over 54. Plug in n equals 4 and you get -46 over 89. Do a couple more. -73 over 134. That's what you get when you plug in n equals 5. And one more. N equals 6. You get -106 over 189. What are these terms approaching? Think of these terms as a sequence. Take the limit as n goes to infinity. What are these approaching? -3/5. Yeah, this is a rational function. The degree of the numerator and the denominator are the same. So the terms are approaching the ratio of the leading coefficients, -3/5. So after a long, long time, you're basically going to be adding -3/5 plus -3/5 plus -3/5, right? Really, really close to -3/5. So what do you think? What does this add up to, a finite number or an infinite number? Thoughts? It's got to be infinite, right? If you just keep subtracting 3/5 from something, it's going to go down and down and down and down, and it's not ever going to be leveling off, right? So this has to add up to negative infinity. So we would say this diverges. This sum has to diverge. And it has no chance of converging because it fails what we call the nth term test for divergence. It says that the limit as n goes to infinity of the terms, if that's not 0, then the sum has to diverge, right? The only way it could converge is if the things that you're adding each time you add something else is super, super small. Those things have to be approaching 0. That's not enough to conclude convergence. It's a necessary but not sufficient condition, right? The terms have to go to 0 for it to have a chance to converge. So these terms are not going to 0, so it fails the nth term test for divergence. So I'm going to write that conclusion right here. Conclusion. This sum diverges because its terms don't approach 0. If the terms don't approach 0, it diverges. All right, let's look at an example where the terms do approach 0. This is called the harmonic series. It's 1 plus a half plus a third plus a fourth plus a fifth. So the terms are going to 0, right? So let's investigate whether or not it converges. So it's called the harmonic series because the, quote, overtones of a vibrating string have wavelengths of a half, a third, a fourth of the fundamental wavelength of the string. Just a little tidbit there. All right, so despite the fact that the terms of the harmonic series approach 0, we can't rule out convergence, but we can't conclude either way. Okay? So it turns out that the harmonic series diverges. It means that when you add up all the terms, you get infinity. So we're going to informally convince ourselves of that by approximating the integral from 1 to infinity of 1 over x dx with left rectangles. Okay? So this is the sum of 1 over n, and we're looking at the integral of 1 over x to help us figure this out. So I want to use left rectangles to approximate this. So if I draw left rectangles starting at 1, oops, I'll do that last bit. Oh, no. Okay. Let's look at the areas of these rectangles. This first rectangle, it has a base of 1 and a height of 1, so its area is 1. This next rectangle, base of 1, height of a half, so its area is 1/2. The next rectangle, it has a base of 1 and a height of 1/3, right? Because that is the value of the function at the left endpoint. 1/3. This one's 1/4. This one's 1/5. This one's 1/6, etc. Right? So if I add up all the rectangles, I get 1 plus a half plus a third plus a fourth plus dot, dot, dot. Is that more or less than the area under the curve from 1 to infinity of 1 over x dx? More. All those rectangles are above the curve. So this is larger than the integral from 1 to infinity of 1 over x dx. What do you know about the integral from 1 to infinity of 1 over x dx? It diverges. Yes, we know that that area is infinite from the material that was on the previous test, right? So this is infinite. So my sum, 1 plus a half plus a third plus a fourth, is larger than something infinite, which makes it also infinite, right? So this sum must diverge. The sum from n equals 1 to infinity of 1 over n diverges. So despite the fact that those terms go to 0, it diverged. Necessary, they have to go to 0, but not sufficient. That doesn't mean you can conclude convergence. All right, another one where the terms go to 0. I'm going to look at the sum of 1 over n squared, and I'm going to figure out whether it converges or diverges by comparing it to a known integral. I'm going to look at the integral from 1 to infinity of 1 over x squared. This time I'm going to draw right rectangles to approximate that integral. So right rectangles, if I start at 2, there's 1, 2, 3 rectangles. Okay. So the area of this rectangle, its base is 1 and its height is a quarter. So this is 1/4. The next rectangle, its base is 1. Its height is 1 over 3 squared, 1/9. Because my function is 1 over x squared now. This is 1/16, 1 over 25. 1 over 36. I'm not going to write it in because I don't have space. So I have the sum 1/4 plus 1/9 plus 1/16 plus 1/25. Are those rectangles, when you add them all up, more than or less than the area under the curve from 1 to infinity? Less than. All those rectangles are below the curve. So this is less than the integral from 1 to infinity of 1 over x squared dx. And what do you know about the integral from 1 to infinity of 1 over x squared dx? It converges. Yeah, we know that that integral converges. So my sum is less than something finite, which means it must also be finite. Why do I keep making an I? N equals 1 to infinity of 1 over n squared converges. Everybody convinced? Okay. All right, so we should be convinced that the sum of 1 over n squared converges to some finite number. We have no way of knowing what that number is. And Euler found that that sum is actually pi squared over 6. That's crazy that it adds up to an irrational number. Add up all these fractions, rational numbers, and you get something with pi in it. So the informal arguments we made about 1 over n and 1 over n squared, those are formalized in something called the integral test. It says, suppose that the terms of your sum, a sub n's, are just functions where your inputs are whole numbers. Right? You have some function that matches your terms of your sum. But f has to be decreasing and positive for the integral test to apply. So it worked both for 1 over n and 1 over n squared, because 1 over x and 1 over x squared are both decreasing and positive. And if that holds, then you can say that if the integral converges, the sum also converges. And inversely, if the integral diverges, the sum also diverges. So let's use the integral test formally to determine convergence and divergence of my two sums. So for 1 over n, we would have to say, since 1 over x is positive and decreasing for x is bigger than or equal to 1, right? Because when you're negative, 1 over x is negative, when x is negative. But we only care about x is bigger than or equal to 1, because those are the sums. I'm starting my sum at n equals 1. So 1 over x is positive and decreasing for x is greater than or equal to 1. The integral, I'll say, and the integral converges. And the integral diverges. The integral of 1 over x dx diverges. So must the sum of 1 over n. One over x satisfies the correct properties, so the sum does what the integral does. So conclusion, therefore the original series, the sum from n equals 1 to infinity of 1 over n, diverges by the integral test. And a very similar argument would be used for 1 over n squared. Since 1 over x squared is positive and decreasing for x is bigger than 1, and the integral converges, so must the sum. So my original series, the sum from n equals 1 to infinity of 1 over n squared, converges by the integral test. All right, so next class for one of our other tests, we're going to need to be able to find some limits at infinity. So we're just going to do some algebra practice right now that will make it easier to digest the big picture next class if you've already done the detail work today. So this is really just some algebra practice, finding some limits. So I want to take the limit as n goes to infinity of this complex fraction. So this is the limit as n goes to infinity. So if you divide a fraction by a fraction, that's the same thing as multiplying by the reciprocal. So I'm going to simplify it by doing n over 3n squared plus n plus 1 times n over 1, instead of dividing by 1 over n. And then just simplify this. We have the limit as n goes to infinity of n squared over 3n squared plus n plus 1. Now this is a rational function. The degree of the numerator and the denominator is the same. So you take the ratio of the leading coefficients and you get 1/3. Not so bad, right? Okay, so for this next one, same first step. I'm dividing a fraction by a fraction. Start by doing the flip and multiply. So this is the limit as n goes to infinity of n plus 1 squared over 2 to the n plus 1 times 2 to the n over n squared. So the 2 to the n over 2 to the n plus 1, they have the same base, right? Dividing like bases, what do you do with the exponents? Subtract. So where is when you do n plus 1 minus n, you get 1. We're going to have a 2 to the first. Where should it go, the numerator or the denominator? The denominator, yeah. There are more 2's in the denominator, n plus 1 of them, than there are in the numerator. So when you cancel, the 2 left over is going to go in the denominator. All right, so this becomes the limit as n goes to infinity. This cancels 1 and 2. So I have n plus 1 squared over 2n squared. I'm going to square that. I'm going to multiply out that n plus 1 squared. You get n squared plus 2n plus 1 over 2n squared. Now this is a rational function. The degree of the numerator and the denominator are the same. When you take the limit as n goes to infinity, you do the ratio of the leading coefficients. So you get 1/2. Last one. Now we've got some factorials thrown in here. We just talked about factorials like 2 or 3 classes ago. So we're going to use what we learned there and our simplifying fraction techniques to take this limit. So we have the limit as n goes to infinity. Same first step, flip and multiply. So I have 4 to the n plus 1 over n plus 1 factorial times n factorial over 4 to the n. So 4 to the n plus 1 and 4 to the n, right? We're dividing like bases. You subtract the exponents. N plus 1 minus n is 1, so I'm going to have a 4 to the first left over. Should I put it in the numerator or the denominator? The numerator. There are more 4s in the numerator than the denominator, so I'm going to cancel that. So that becomes 4 to the first. That becomes 1. All right, so now I need to figure out how to simplify the factorials. So I think I'll just write down, I have 4 times n factorial over n plus 1 factorial. All right, so I mentioned when we did this a couple classes ago that we start with the larger factorial. But I think I'm just going to write out the factorials. So let's see, 4. N factorial, that means n times n minus 1 times n minus 2. And I keep subtracting 1 until I get to 1. That's the definition of factorial. So 4 factorial is 4 times 3 times 2 times 1. You just keep subtracting 1 until you hit 1. And you multiply them all together. And then n plus 1 factorial, you start with n plus 1. What's 1 less than n plus 1? N. And then 1 less than that is n minus 1, n minus 2. Keep going until you do times 2 times 1. Now I'm going to cancel common factors. N, n minus 1, n minus 1, n minus 2, n minus 2. 2 and 1, 2 and 1. So this is the limit as n goes to infinity of 4 over n plus 1. What happens as n goes to infinity? It goes to 0. Yeah, because the denominator is going to get really, really big, which means the value of the fraction gets really, really small. So my limit is 0.